Welcome to the first this year's talk for this semester. Very fortunately, we can invite one of our outstanding junior faculty members to give a cutting-edge talk. Okay? The talk title is Accelerating Scientific Data Compression with Advanced GPUs. Okay? The title is very straightforward and very intuitive. Okay? When we say outstanding, we don't care if that person is tall or short. We only care if that person has a long scientific shot. Meaning, if that person's work has big impact on his or her areas. All right. That's why I'm 100% sure I can use the term outstanding today for our speaker. All right. I don't think I have to introduce the abstract of his talk. His talk will show you, the cutting-edge approach in this area here. So let's welcome our outstanding speaker today for this semester, Dr. Xin Liang. All right.
Hello, everyone, and thanks, Dr.
One second. Unfortunately, we don't have pizza today. But you can come back, at 5 to join the department picnic, right? So make sure you remember that you need to come back at 5. All right, it's yours, all yours.
Okay. Thanks, Dr. Chen, for the invitation and the nice introduction. So today I'm very happy to share my recent work on scientific data management with advanced GPUs. Basically, we will introduce a little bit on the architecture of the GPU and the common optimization techniques, and finally, how we can apply it in our specific area to advanced science. So, first question, why do we need the compression? Because our goal of the talk here is to introduce how to leverage GPUs to accelerate the compression. So the first question is, why do we need compression? So this is due to the fact that scientific applications generate data at an unprecedented amount and speed. So here are 3 very typical examples from DOE national laboratories. So the first one is called the HAT cosmology simulation. Basically, in this simulation, it needs to be run on a supercomputer. And if you want to simulate a 1 trillion particle, this will produce 20 petabytes of data. So as you may know, 20 petabytes is something like the 20,000 of terabytes. So that's really a huge amount of the data. As another example, the E3SM climate simulation, which is developed by the NCAR, this will produce 20 terabytes of data every 16 seconds. Below the order of the data is several magnitudes of lower than the HAT simulation, but its generation speed is extremely fast. So consider the simulation will be run for several hours. So this again will produce petabyte of data. So the next example is the fusion simulation. So this is used in PPPL, which is the physics national lab. Basically, this kind of simulation is to study how we can construct the future fusion reactors. So they will study how the particle moves inside the fusion reactor to find out how to make the correct construction. So this kind of simulation is expected to produce data at 1 exabyte per day. So exabyte is something like the 1,000 petabyte. That's a great magnitude of large amount of data compared to the HAT and the climate. So basically, as we can say, those kind of scientific simulations are producing real large amount of the data, and how to effectively manage those kind of data remains an open problem. So another reason is that we produce so much data and we need the mechanism to store and transfer it. However, the current advance in the I/O and storage system cannot keep up with the advance of the computing speed. So here are 2 very typical limitations we can say from today's cutting-edge computing system. So this figure just shows the recent upgrade of the leadership computing facility from Oak Ridge National Lab. As we can see from the figure, if we look at the update on the storage and I/O from Titan to Summit, there is 2.5 times improvement in the I/O performance, but there is X times performance in the computing speed. Similarly, if we look at the upgrade from Summit to Frontier, there is only 2 to 4 times speed up in I/O compared with the 8 times in computing. With that being said, we can say that we have more and more computing powers to generate a large amount of the data, but our storage and I/O systems cannot keep up with that speed. So for a typical example, if we look at the specifications for the Frontier supercomputer, which was the #1 in 2022, so there is a very high computing to I/O ratio. Basically, it will have 1.6 exaflops per flops computing speed. So a rotation on the unit here. So in order to measure the performance of the computers, we have the metric which is called flops, which is a short for floating point operations per second. Basically, if you have a higher number of flops, you have the higher computing performance. So the Frontier has a 1.6 exascale flops performance. But it only has 10 terabytes per second I/O speed. So with this kind of computing to I/O ratio, you have to perform 1.28 million floating points per second for each double data you fetch. So this is usually not the case for many of the scientific applications. So I/O remains a bottleneck in the leading computing systems. So when we talk about compression, one of the direct ideas is just to leverage lossless compression, which is widely used in many applications such as database. However, one of the problems of the traditional lossless compression is that it cannot do much for scientific data, which is usually in floating point format. So the right figure just shows the typical visualization of the typical scientific data in floating point representation. As we can see, the mantissa of the floating point data really looks like some random noise, which is extremely hard to compress. As a result, if you compress floating point scientific data with the corresponding lossless compressor, it will lead to a compression ratio that is usually less than 2. So this is far from desired. As we can see, the previous I/O gap is much larger than 2. So alternatively, one can take the lossy compression to complete the task. So this can bridge the gap a little bit, but it may not be able to completely solve the problem. So lossy compression provides the trade-off between accuracy and compression ratio. Basically, this is tunable. If you need the higher compression ratio, you may sacrifice the accuracy a little bit. And it is able to provide multi-scale representation, which will be very effective for scientific analysis, that has some complexity, which is a portion of the size of the data. So, however, if we directly apply the traditional lossy compression to scientific data, it may raise some serious concerns on the quality, because scientific analysis require high accuracy in particular region of the data to figure out some scientific findings. In that case, we have to guarantee the fidelity of the data. Otherwise, this will lead to some probably wrong discovery or wrong findings. So in this case, it will hinder scientific discoveries instead of advance it. So in order to mitigate this problem, so existing research just propose a new idea. Basically, they propose to add error control to general lossy compression technique to ensure the fidelity of the data. So this kind of approach makes sure the distortion of the decompressed data and the original data will be bounded by some specific metric. In this case, the data can be trusted for some of the scientific analysis. So the figures shows 3 typical scientific lossy compressors, namely SA, MGuard, and ZFP. So basically, they are widely used in scientific applications to advance the scientific data management. So most... yeah.
You said that varying compression ratio from 1 on the left to 250 to 1 on the right. Which left, which right?
Yeah, I think this one is 10 to the 1, because if you have lower compression ratio, you say the data is more smooth, so you say the details. If for this one, it's around 250. Basically, if you take a closer look, you can see some. No, this figure, only this one. Probably you cannot see it. So this one, so only this one shows the varying compression ratio, the one on the top. So basically, on the left, you can see the smooth details of the data. But on the other side, you say it's a little bit, it looks like not smooth at all because you lose some information during compression. So the figure on the top. So the traditional approach of the lossy compression is usually CPU-based, but this can cause some problem in the cutting-edge systems. So one of the reasons is that the CPU-based compressors have a relatively low computing performance compared to the I/O speed. So as we can see in the figure, so this is our recent paper in 2021. It just compared the computing performance of different lossy compressors. As you can see, the fastest lossy compressor using a CPU load can lead to up to 1 gigabyte per second throughput. So this is much less than the several terabytes per second I/O speed in the cutting-edge systems. As a result, you need to employ over thousands of CPU cores to catch up with the I/O performance. And in order to beat the I/O performance to get some real benefit, you even need more number of loads to achieve that. So this becomes a serious concern for lossy compressors because one of the ultimate goal is just to advance the scientific management task, including improving the I/O and data transfer. So on the other hand, so basically the new trend in constructing the leading computing systems, such as the large-scale supercomputers, is to leverage GPUs. This is inspired by the large computing power provided by general advanced GPUs. So as we can see in the figure, so this lists the top 3 supercomputers in the world, which is updated in, I guess it's updated in the June of this year. So the top 3 supercomputers are all GPU-based systems. That is to say, they employ a lot of the GPU powers to aggregate, to get a very high aggregated computing performance. So with this kind of a system, if you focus on CPU-based implementation, this will severely overlook the potential power of the GPUs in this system. So after looking at the reason for study GPU-based compression, let's just look at the typical difference between CPUs and GPUs. So usually, CPU is latency optimized, and it is very adept at the sequential tasks. As a result, it has lots of big on-chip caches to enable high bandwidth of the data. And also, it has very sophisticated control and branch prediction in its design of handling instructions. As you may know, you may have some out of core execution in the CPUs to get some performance gain. For example, the speculations. However, those kind of things may require a lot of overhead to recover if you have a wrong prediction. So this is for GPU-based tasks. For GPUs, it's more throughput-oriented. Basically, it may not lead to very low latency, but it will have a very high throughput. Basically, for GPUs, as we can see in this figure, it has a lot of arithmetic logic unit. So this will enable a high performance for computation. And the GPUs enables SIMD, which is leverages SIMD, which is single instruction, multiple data, so that you can accelerate the performance of typical instructions. So the figure on the right shows the specifications of the latest CPUs and GPUs. As we can see, so for the general Intel-based CPUs, for a single core, it can have a performance of roughly 1 teraflops. However, the latest H100 from NVIDIA can get a performance of over 4,000 terabytes. So there is a very large performance gap between CPU and GPUs, which motivates the use of GPU if performance is one of the ultimate goals. So a little bit more on the GPU architecture so that we can understand better on how we can leverage GPUs to accelerate our task. So basically, GPU have a thread hierarchy as noted in the figure. Basically, the minimal unit of GPU is a thread. Each thread will handle a piece of the data and the corresponding instruction. And it has a block design in which one of the blocks may contain multiple threads. At last, it have a grid where each grid consists of multiple blocks. So those kind of thread hierarchies give you the information on how to arrange tasks using GPU. So when you design GPU algorithm, you should take that into account to get high performance. Another term to note is the warp. Warp is the minimal execution unit for GPUs. Basically, all of the threads inside the warp have to execute the same instruction to follow in the SIMD paradigm. Basically, if there is a difference different instruction in different thread, it has to be scheduled into different execution times. So basically, in order to get high performance with GPUs, you have to have the same execution instruction inside a single warp. In addition to that, another aspect in GPU is the memory hierarchy, which is also very important for gaining performance. Basically, the hierarchy is a little bit similar to CPU, but it differs on several aspects. First of all, it has a relatively large register file so that it can hold multiple variables. And in addition to that, GPU have a shared memory, which provides much faster data access than the global memory. So the constant textual memory is used to hold some of the constant data, which is not usually used in our scientific data domain, but it may be used for some of the graphic tasks. And in addition to that, GPU have a local memory, which have similar access speed compared to the global memory. And it has a L1, L2 cache, which is smaller than those in CPU, but it can offer considerable data access performance. So the figure on the right just shows the typical hierarchies of the memories, and the figure on the left shows the latency of different memory schemes. So as we can say, so if you put data in shared memory, it will be much faster than accessing the global memory. As a result, so basically leveraging shared memory is an important optimization for GPU-based applications. A little bit more about the typical optimizations, though. So with a data reduction example, so this reduction is a little bit different from the data reduction we talk about. So for reduction, it means we want to compute the sum of an array. So this is a very traditional example from NVIDIA, but I think it is very useful because it covers most of the optimization techniques we will say in GPU-based applications. So I would like to mention it a little bit so that you can be a little bit more aware of that. So for this task is super simple. Given a specific array of data, the goal is just to compute the sum. So in order to handle the large amount of the data in an array, for example, you may have over 1 million of data in the array. So in this case, you may not be able to assign each thread to one data element. So in this case, you may need to launch multiple kernels and merge the results accordingly. So basically, this just enables the two-level design of the data reduction example. You may have different thread block to handle a portion of the data, and finally, you will perform another reduction on the reduced samples to get the final result. So this is the problem, and we will say a little bit about the optimizations. So one of the direct way to implement this algorithm is just to assign the ith element to the ith thread. So each thread will handle one of the corresponding elements to perform the reduction. So as we can see in the figure, this figure on the left just shows how GPU assigns different threads to different data in this implementation. Basically, in the first step, only the even number of threads can handle the data because the odd number of the threads will do nothing. So in this will lead to a severe problem called branch divergence. So this is related to what we mentioned about the warp execution following the SIMD paradigm. So if you have this kind of a branch, that is to say, for some of the threads, you need to do something. For the other of the thread, you need to do some other things. So this kind of a divergence inside a warp will lead to double times of the execution time because portion of the thread will be masked due to the different instructions. So inside a warp, all of the threads has to execute the same instruction. So in order to optimize this one, so basically one can arrange the thread assignment a little bit. So originally, as we can see from the figure, the S data will be assigned to the S thread that lead to the branch divergence. However, what we can do is that we can assign the thread based on the available task. So in the first iteration, we will only assign the task to the even number of threads. So in this case, all the threads will perform the same task to enable SIMD. So for this kind of optimization, it can significantly eliminate the divergence inside a warp, but it will raise new problems, which is called the memory bank conflicts. So this occurs when the threads inside the same warp, so usually 32 threads, access some memory regions. So assume all the threads are accessing different regions of the data, so as shown in the top figure. So if all of the threads are accessing different and/or continuous memory regions, so there is no bank conflicts. So the memory transaction can be done in one time. However, if you have some conflict on the same bank, so they have to be serialized to avoid the bank conflict. So in the example shown in the bottom, you can say, although they only access the same amount of the data, so the example on the bottom will cause 3 times of the memory overhead because of the bank conflict. So in order to avoid this, basically one can perform the so-called sequential addressing to eliminate the bank conflict issue. Instead of assigning the original thread in the previous approach, one can adjust it a little bit to avoid the bank conflict. Basically, the first thread will be responsible to add its own number to another number, which is half a block away. In this case, it just can eliminate the bank conflict. So there are some additional optimization we can use in this example. One of them is to replace the load operation, and the other is to use the loop unrolling to further enhance the performance. Basically, those kind of techniques are very common in GPUs to improve the performance. So if you compare the performance of the different approaches mentioned above, you can see a significant difference in the resulting performance. So the final optimized kernel, which involve all of the optimizations, will lead to 15 times performance gain compared to the naive implementation. This just tells us if we cannot handle the GPU implementation properly, we may not be able to find to achieve the proper performance gain. So the GPU, in my opinion, so the optimization techniques in GPUs are pretty similar, are pretty common, unless on some specific architecture such as the tensor core. So if you have some new architecture, you may have a new optimization technique. But the general optimization techniques in GPUs is very common. So usually they are something like the avoid divergence, bank conflict, and how to improve the memory bandwidth. So all of those kind of techniques are known to the GPU expert. But the research on GPU-based acceleration is that after identify a research problem, how can you convert this kind of problem to a GPU-compliant form to fully leverage the power of the GPU? That's a real question. So then let's just look at how we can leverage that optimization to advance our scientific data compression. So most of our work is based on the SA lossy compressor, which is a general error-bounded lossy compression framework. Basically, it provides a prediction-based compression pipeline for users to compose different compression algorithms. So there are different variations of SA, but we will focus on the traditional one, which is the prediction-based pipeline. So for this kind of compressors, there are 4 key steps. The first one is called prediction. So basically, you will leverage the correct correlations in the data to make good approximation. So only if you have very good approximation on the data, you can achieve very high compression ratio. So the second stage is called quantization. So this will discretize the prediction errors in the original data. So after you make the prediction, which provide you an approximation, there is an error between the approximation and the real value. So in the quantization stage, we need to quantize the error from the floating point data format to integer data format to reduce the entropy. And meanwhile, we need to ensure error control to make the data usable for scientific applications. And in addition to that, we will have an entropy encoding step, which leverages entropy encoders to reduce the size of the data. And at last, all of the data will be fed to a lossless compressor to further reduce the size. So the figure below just shows the pipeline of error control, the lossy compression, and the traditional lossy compressors. So the traditional one, so basically you only perform decorrelation and encoding to generate the compressed data. So for error controlled compression, one of the key steps is just to leverage the quantization techniques to reduce the entropy of the data while ensuring the errors. So the prediction stage in SA will have multiple predictors, but in this talk, we will mainly introduce two of them and see how we can optimize them using GPUs. So the first predictor is called the Lorenzo predictor. This is proposed in the first release of SA. So for this kind of predictors, it just assume a polynomial fitting inside a neighborhood. So assume you have a two-dimensional data as shown in the figure A. So basically, it assumes all of the four data lies in the same linear function. Then you can determine the value of the function using the three known data. And then after loading the function, you can use it to predict the last data. So this is the Lorenzo prediction. Basically, you need to decode you need to predict the data one by one during the execution. So this raises severe problem in the GPU implementation because, as we said, GPU will require the highly parallelism inside the execution task. However, for this kind of approach, you need to process data one by one. This heavily slows the procedure of parallelization. So another predictor used in SA is the interpolation predictor. Basically, it leverages some traditional interpolation mechanisms, such as cubic spline fitting, to approximate the data. Again, they have different prediction results or efficiency, and they have a different level of parallelism that we can exploit. So the second stage is called quantization. Basically, it employs the linear scaling quantization to have error control on data. So for those kind of, for basically giving a prediction difference, SA will compute the number of shift intervals to reach the corresponding original data. So this will turn the original error to an offset of the intervals, which is an integer. This significantly reduces the entropy of the data, and it ensures the difference between the original data and the predicted data after the shift is within some error bound. So at last, SA will feed the quantization index to lossless encoding modules, including a Huffman tree and some other lossless encoding algorithms. So for the Huffman tree, I believe most of you are familiar with that. Basically, in Huffman trees, we construct in Huffman encoding, we construct the Huffman trees based on the frequency of the data. And then following the Huffman trees, we can tell which kind of code can be used for which data. For example, for the 19 here in this example, the Huffman encoder will be 111, which is the path from the root to the corresponding leaf. So this is the Huffman encoding. And at last, there is some other lossless encoding using gzip or the standard. Those kind of lossless encoding steps are actually part of the steps has a very high sequential dependency. So how to fit those kind of algorithms to GPU is still an open challenge. So after introducing the basic mechanisms of the CPU-based compression algorithm, we then talk about how we can leverage GPUs to improve the performance. So our first work on this series of work is the QSA, which parallelizes the Lorenz predictor in the traditional CPU-based compressors. So one of the key contribution we made is to eliminate the read after write dependency in the Lorenz prediction using a proposed strategy called dual quantization. Basically, this eliminates the heavy dependency in the Lorenz prediction task to enable high parallelism. And in addition to that, we also propose a customized Huffman encoding strategy to change the quantization index to compact size for better processing speed. Those kind of techniques heavily improve the performance of GPU-based implementation. So the figure below shows the basic design of our QSA framework. So originally, if you have the original data, we perform a pre-quantization stage. So basically, originally, as we mentioned, we have the prediction followed by quantization and the lossless encoding. Here, we specifically have a pre-quantization stage to quantize the data, and we make prediction after the pre-quantization. After that, we perform another post-quantization to generate the quantization index. So originally, if you have the original data, we need to predict the data one by one. We predict one data, compute the quantization index, recover the data, and perform another prediction. So those kind of things is highly serial, which lead to low performance. So basically, in our optimized algorithm, we first quantize the data and then perform lossless prediction across the data in a parallel fashion. In this case, we gain high performance. And in addition to that, we also optimize the Huffman encoding strategy. Basically, we build and canonize the Huffman codebook and use a fixed-length Huffman encode to get the better performance. So that's a key improvement we made in designing and implementing QSA. So a little bit more on how we parallelize the Lorenz prediction. So basically, we made several optimizations as listed below. So the first one is that we apply a specific data parting and chunking operation to unify the operations inside a block. So originally, if you perform the Lorenz prediction on the original data, you may have branch divergence on the borders, because for the border element, it does not have sufficient number of labels to perform the same kind of operation. And the branch divergence inside a GPU whirlpool will lead to low performance, as we mentioned before. So in this case, we just apply a parting to the data such that the data can be processed in the same fashion. So after increasing the one row and one column of the data, so all of the data operations in the block can be unified to the same fashion. So in this case, we can leverage GPU to achieve higher parallelism. And in addition to that, we also perform the dual quantization strategy as mentioned before. So instead of the traditional technique, which performs the prediction, quantization, and data recover one after another, we first perform the quantization and then perform the prediction in a parallel fashion. So this will give you better performance compared to the traditional sequential execution. So in addition to that, we also optimized the Huffman encoding by optimizing different steps in this stage. Basically, we optimize the histogram for quantization bins. In this step, we just collect the frequency of the quantized data to build the Huffman tree. So in this specific stage, we use replicas to reduce the conflict inside the memory, and we leverage the shared memory to achieve high bandwidth. So this typically generates higher data processing speed. And also, when construct the Huffman tree, we improve the bandwidth with the adaptive code word representation. Basically, based on the quantization index we have, we use different data types to represent data during the construction. This will give you the better performance when you can use a low number of bits to represent the data. In addition to that, we also use canonizing Huffman codebook to have efficient decoding. So this kind of algorithm just maps the original Huffman encoding to a new format, such that it can maintain the same number of bits for each data, but it just follows a specific order for the designing. So using this kind of a strategy, you can avoid reconstructing the Huffman tree during decompression, which is a serial procedure that needs to be eliminated in the parallel execution. And finally, we also use coarse-grained parallelization and chunk size optimization to further improve the performance. So this figure just shows the performance we achieve using QSA compared with the traditional assay. Basically, if you look at the figure on the right button, you can see the performance gain. Compared to the CPU implementation in a single load, basically the QSA implementation can deliver hundreds of speed up. So basically, even if you optimize your CPU code using OpenMP, which is a shared memory optimization, our QSA-based approach can deliver over 10 times of throughput. Basically, this significantly improves the performance of scientific data compression to facilitate its use in scientific applications. So this is the first work we have done to accelerate the compression approaches. And then further, we optimize the QSA-based design to improve the performance using additional optimizations. So this kind of approach addresses two key limitations in QSA. First of all, in QSA, we have limited compression ratios because as we mentioned, we applied Huffman encoding on the quantized data, but in QSA, we ignore the lossless encoding such as gzip and Z standard, which is highly serial, but can improve the compression ratios. So in QSA Plus, we just incorporate the pattern-based lossless encoding to improve the compression ratios. Another limitation in the previous QSA is that it has limited decompression performance due to the sequential construction of the predictive values. So we didn't mention it in the previous slides, but I can elaborate a little bit. Basically, in the original QSA, what we do is just to parallelize the prediction stage using the dual quantization. So this can significantly improve the performance during compression, but it may have little benefit in decompression. The reason is that in decompression, you do not have the original data, so you cannot perform the dual quantization strategies. So in QSA Plus, we just improve this issue by proposing a different prediction scheme for the Lorenzo-based predictors, as we can see later. So the figure below just depicts the design of the QSA Plus compared with QSA. Basically, we improve the performance of Lorenzo construction, quantization, and Lorenzo reconstruction. And in addition to that, we apply a random encoding with optional variable length encoding to further improve the ratios after Huffman encoding. So this figure this slide just depicts a little bit details on the approach. Basically, what we do is to first apply the random encoding to achieve the better compression ratio. So this is guaranteed because you just use an additional stage to further analyze and compress the data. And in addition to that, we optimize the Lorenzo prediction on GPUs using the approaches below. First of all, we increase the number of the thread blocks in a single streaming multiprocessor with a new data assignment. So forgot to mention, streaming multiprocessor is a execution unit inside the CUDA. Basically, a streaming multiprocessor will execute multiple works. And also, we eliminate the divergence for outlier process to enable final parallelism. This is also very important because in the traditional design of QSA, when one of the data falls out of the quantization intervals, so we have to process it separately. So this requires a specific handling strategy for those kind of outliers. And these outliers scattered around the original data, so they are not clustered. So in this case, it will lead to branch divergence in multiple regions, which will slow the performance. So what we did is just to eliminate the divergence to better process those outliers. And at last, we reformat the Lorenzo prediction to a prefix sum operation. So, and then we implement it with coalesced memory access and balanced load store and computation. So in this case, it can deliver higher performance during the decompression stage compared with the QSA. And this figure just shows the improvement we have made compared with the original QSA. Basically, if you look at the figure on the right top, we have a slight improvement on the compression performance because we optimized several of the stages. And we have some significant improvement on the decompression stage because of the new design for Lorenzo predictor. So this is because we use the prefix sum operation to get higher parallelism than the traditional sequential access. And this also shows the comparison on different stages. Basically, this just summarizes the performance on different stages, and you can see the bottleneck of each stages to say which is the future optimization target. So this is the QSA plus, and after that I will introduce another compressor which is called FZ-GPU. So this is also based on QSA, but it differs a little bit on identifying the task. So as we mentioned before, the techniques in GPU optimization is very common. So the difficulty is just to identify the proper region of your code to say which is suitable for GPU parallelization and how we can implement that effectively. So for the FZ-GPU, it just tackles a different stage of the original QSA design. So in QSA plus, as we mentioned, so basically we mainly optimize the Lorenzo prediction stage. So that is one key stage in the compression. But it just overlooks the encoding stage. So in the QSA or QSA plus, we always use a Huffman encoder that is highly serial or sequential in construction of the Huffman tree. So this remains as one of the performance bottleneck. So in FZ-GPU, what we propose is just to replace the Huffman encoding with another lossless encoding strategy to achieve higher parallelism. So the detail is as follows. So first of all, the key idea in FZ-GPU is just to leverage bit shuffle and the corresponding encoding strategy to improve the throughput of the whole entire pipeline. So basically, for the encoding stage, what FZ-GPU does is to first apply a bit shuffle on the quantization integers and then record the data one block by block. If you encounter a block of all zeros, you just skip that block and mark a specific sign on that. So this kind of a simple strategy may lead to lower compression ratio than Huffman trees because, as you may know, Huffman tree is near optimal construction, near optimal in reducing the entropy, but this kind of approach is not. But this kind of approach can lead to higher parallelism that you can achieve on GPUs. So basically, we apply several optimizations. The first one is just to, again, avoid the spatial handling of the outliers due to the use of the encoder. So originally, we mentioned the outliers in the Lorenzo predictor. It can lead to warp divergence, which may slow the performance. And we optimize it a little bit on the QSA plus, but it does not fully eliminate the problem. In FZ-GPU, we fully remediate this problem by leveraging a new encoding design. So we no longer need to process the outliers to get high parallelism. And in addition to that, we modify the data format of the negative integers to complement our encoding strategy. Basically, we do not use the choose complementary to represent the negative data. Instead, we use a sign bit to record the sign and record the rest of the integer as it is. So this is the first optimization we did on dual quantization. And the key contribution we made is the lossless encoding module, which provides optimization on bit shuffling and a new lossless encoding algorithm. So we propose to use bit shuffle to rearrange the data such that more zeros can be continuous. The zeros can be continuous. So if the zeros is continuous, we can use a sign to represent a block of the data, which can give you high compression ratios. So however, bit shuffle, so the operation of the bit shuffle is as follows. Basically, you have the data as here. Assume you have you have this number of data. Each data has 16 bits. after bit shuffle, you just represent it in this way. So in this kind of a representation, you can accumulate the zeros in the original data to achieve higher compression efficiency. So basically, however, this one is not very optimized on traditional GPUs. So in order to achieve high performance, we apply three optimizations, which include the use of the shared memory to reduce memory access. We also use a warp level synchronization function to get higher speed up. And in addition, we rearrange the output format a little bit to enable coalesced memory access. Again, coalesced memory access is another optimization in CUDA, which provide high bandwidth between shared memory and global memory. So in the original approach, you will have uncoalesced analysis. Basically, when you store the data from the shared memory to global memory, you can say those kind of access is not continuous. So this will lead to uncoalesced access. However, we rearrange the output format a little bit to follow the correct memory access pattern. This just enable higher memory bandwidth. So at last, we basically, based on this kind of bit shuffling design, we apply or utilize a new lossless encoding algorithm to improve the compression ratio. So this kind of implementation usually requires a press-on operation to compute the memory offset of different blocks. And we further optimize the press-on operation on GPUs. So this figure just shows the performance of the proposed approach compared with the traditional one. Basically, as we can say, the FZ GPU can achieve considerably higher performance compared with the QSA and the QSA Plus. However, it may not be that fast as two other compressors, such as QZFP. If you look at the quality of the compression, which is usually represented by the rate distortion figure, so this figure just shows the relationship between the compression ratio and the errors in the data. So if the corresponding curve is to the left and top, so it is better. So otherwise, it is worse. So as we can see from the figure, the FZ GPU may not have the same compression quality compared with QSA and the QSA Plus in some of the dataset, but it does on some of the other dataset. This is because the encoding strategy it leverage is less efficient than Huffman in some cases. So in those kind of dataset, it will not have higher compression quality. However, instead, it just provides better throughput when compared with the QSA. So it will deliver up to, I didn't remember the exact numbers, but basically it's over 5 times improvement in the compression performance. And this figure just shows the different optimization techniques we employ in FZ GPU to get higher performance. So as we can say, so for the pre-quantization, basically for this one, we just eliminate the outlier processing, which gives you the better performance. For the bit shuffle, basically, again, we optimize those kind of performance using coalesced memory access and higher bandwidth in shared memory. This again gives you better performance. So for prefix sum, this is used in the lossless encoding. We further optimize the prefix sum operations, as we mentioned before, which also delivers higher performance. So aggregatedly, so if we employ all of the optimization techniques we mentioned, overall, we can get much higher compression throughput compared with the traditional QSA or QSA Plus. So we also have several other techniques, such as the QSA Lite. So basically for this one, it just optimizes the interpolation stage in this specific pipeline. Basically, it also leverages some of the traditional optimizations, such as coalesced memory access and and the elimination of the divergence to get better performance. Because of limited time, I will skip it a little bit. So basically, this just concludes my talk today. We introduced several techniques on the GPU-based lossy compression approach. So this will deliver higher performance in the compression. And consequently, it may lead to lower compression quality a little bit because we modify the stage of the compression to make it complementary or compliant to the design of the GPUs. So the key point I want to deliver is that, so if you want to use GPUs to accelerate the application, so the difficulty is usually not on the not on inventing new optimization techniques in GPU. The difficulty is that really you want to convert your original problem to a similar problem on GPU. It may trade off the corresponding quality a little bit, but it can deliver much higher performance if those kind of trade-off is acceptable. So if you want to pursue on the GPU-based research, you may have the original problem that require acceleration, and then you can just adjust your approach a little bit to make it parallelizable. This is usually more difficult than investigating or applying the existing optimization techniques. So this concludes my talk, and I'm happy to take any questions.
All right, we have some time for questions.
So thanks for the talk. I have one question. It's basically, in your research, your focus is mainly to reduce the I/O overhead caused by the sequentialized processing in the CPU. And basically, the GPU can give you more parallelized processing capability. But my concern is basically when you move the data from one node to the other node, you want to reduce the size of data by doing this compression. But to do this compression, you need to move the data from the CPU to GPU first, and then over network, and then to the other end. So I'm wondering whether it might be a good idea to do this compression directly in network. For example, there are some in-network devices like the SmartNIC, and although their parallelism may not be as good as GPU, but they have that potential. So do you have any comments on that?
Thanks for the question. It's really a good question. So let me just reiterate a little bit. The question is, because one of our goals is just to use compression to mitigate the data transfer overhead. So because this is of the goal, so would it be possible if we apply this kind of compression procedure on network instead of using the accelerator such as the GPU or using the traditional CPU? That is a really very interesting question, and we are investigating that. So basically, we do not leverage GPU for the on-network compression, but we do consider using FPGAs to do that, because FPGAs can be easily deployed on those kind of networks. So basically, for those kind of implementation, it will require another revision of the algorithm to fit the FPGA paradigm. It's a little bit different on the algorithm, but it will give you some benefit, because in this case, you do no longer need the external accelerators, or you do not need to consider actual handling of those kind of things when in data generation. So you only do that on network. So you put on GPU when sending the data, so it performs the compression. You put an FPGA on the network. When sending the data, it performs the compression. When receiving the data, it performs the decompression. And then this will give you the better performance, and it will just eliminate the use of the compression routines in scientific applications. This is another advantage. Basically, using our approach, you have to insert the compression code in the original application code. That's take a lot of effort, because you know there is tons of code in those kind of applications.
So everything's under CUDA, right?
So for FPGA implementation, I think we tried the open cell, and we have, I think one of the students implemented some Verilog, but I'm not very familiar with that because I do not deal with FPGAs. But definitely, this is a very good idea.
Okay, thanks.
Yeah.
I have a question on the technical side. So you mentioned the lossy compressor. That means usually you input some data and you get some compressed form, and when you recover it, you encounter some loss. I wonder, the loss rate is calculated by some theorem, or it's calculated by some experiment or measurement?
Yeah, that's a very good question as well. So the question is regarding the quality of the data on the lossy side. So basically, we have different mechanisms for the metric. I introduced that in my last year's talk. Basically, there are multiple ways. The first one is the absolute error. So we just ensure if you specify an absolute error bound, we ensure that the difference between the original data and the decompressed data is within that kind of error bound. And we also have other metrics, statistical metrics such as PSNR, to measure the global difference. In addition to that, we also have specific techniques to preserve topological features. So those kind of things also have a different metric. Basically, for example, one of the features is the critical point. So this is in a vector field, it represents the load with zero velocity. So basically, it's usually the center of a hurricane, so it's very important. So for those kind of features, we just ensure it is exactly the same as the original data. So basically, for different tasks, we have different specific mechanism or metric to quantify the error.
Okay, thank you.
Any other questions? We still have a few minutes, right? I have a question for you. I didn't know that Hoffman coding. I only know that Hoffman sells cars. If you're from Frankfurt area, then you would know what I mean. Hoffman, Neil Hoffman, they sell cars. I'm just kidding. So questions? Like I said, we don't have pizza today, but we have a department picnic at 5 today. So welcome everybody to join the picnic at 5, right? We have plenty of food. Any questions?
I guess about the picnic, is it at here at Davis Marksberry?
Yes. Here. Everybody's questions, all right? Any questions? Or you can, ask questions, directly to the speaker after the talk. You said that your performance, you improve traditional approach by 5 times, or?
So basically, compared with the CPU-based approach, so without OpenMP, our performance improvement now can be over 1,000 times.
1,000 times?
Compared with the one-core CPU. So if you have OpenMP, we can get something like up to several, I can think at least tens of speed up to 100 times on a single load.
Well, that's a big improvement.
Yeah, so for CPU, so basically it's a big improvement. So the 5 times is the improvement versus the previous GPU application.
I see. Well, it's a good performance. Any other questions?
Okay, thank you. My question is, to improve the performance of the GPUs in order to support such as the machine learning applications or deep learning applications. But from your work, I didn't see you use those like learning-based techniques and to improve the GPUs. Instead, you use some statistic-based methods. And the reason is because those techniques, they are more efficient compared to the machine learning-based techniques.
So let me check if I understand the question. So basically, you're asking if we can use the machine learning-based techniques to improve do you mean the performance of the compression or the quality of the compression?
Both.
So I will say that if you use machine learning approaches, it will give you a negative performance compared with the traditional approach. Because we have experts on neural network here, so it's, the complexity is very high compared to the traditional approach. So as I mentioned, the Lorenzo prediction, for each data, you only need to fit a polynomial. So basically, this will reduce to very minimal number of operations for one data point. So if you use machine learning approach, you will feed the data to a large neural network, and you will have complex computations inside each layer, and you will also need an extremely long training procedure to produce the model. So those kind of things are very negative on the performance side. However, it may deliver some better quality in terms of compression, especially when your requirement on the error is not very high. So in our previous study, we have tried to apply deep neural networks to make the approximation. So as we mentioned, the key step is always the approximation. And the machine learning is good at approximation. However, as we said, if you have no error tolerance, so such as an absolute error bound of 10 to the negative 5, if you have those kind of requirement, machine learning approach is not very good. If you have an error requirement, something like the 10 to the negative 1 or 10 to the negative 2, machine learning is good because it's very good at smoothing data. So basically, based on our current research, we will advocate the use of the machine learning techniques with lower error constraint. But we will switch to the traditional method if you have higher error constraint.
Thank you very much.
You're welcome. And also the optimization of techniques using GPU is also another widely studied topic. So if you are interested in that, basically you can look at different approaches. The first one is to directly improve the performance. So you can decompose the machine learning operation for deep neural network. You can decompose those kind of operation to metrical multiplications. And the metrical multiplication is highly optimized on GPU in existing libraries. And in addition to that, there are additional approach to fit the original very large model inside a single GPU. So original GPU has a fixed memory such as 80 gigabytes. It may not be able to execute the entire model. So the existing approach is just use some offloading approach to offload some of the computing tasks and the memory to a CPU. So you will have a constant data transfer between CPU and the GPU and hide the transfer cost by overlapping it with the computation. So those kind of techniques are used on GPUs to advance machine learning. Yeah.
All right, just one last question.
Yeah.
Okay. Is there a difference between compression pictorial data sets and texture-based data set? Is there a difference performance-wise?
That's a very good question. So actually, I will think there will be difference. So we did some initial experiment on comparing that. So if we apply JPEG on our scientific data, it may not be as good as our compressors. So if we apply our techniques to image data, we may not be as good as JPEG. So I do think there are specific strategies. And there are similar parts. For example, for JPEG compression, they just use discrete cosine transform and coupled with bitplane encoding. So those can be specifically good at handling image data. But for scientific data, we find that if we want to perform transport, discrete cosine transform may not be the best one. You have other transform may give you higher compression quality.
All right, we thank the speaker again for this very